So we have physics PhD qualifying exam practice problem number 16 in electricity and magnetism domain. So let's begin. A classical charged particle of charge Q and mass m moves under the influence of an external force F sub ext of t equals F naught e to the negative gamma t x hat. The particle experiences radiation reaction described by Abraham-Lorentz equation ma equals F sub ext plus q squared over 6 pi e naught epsilon naught c cubed a dot. Part A, solve the differential equation for acceleration a of t and obtain the general solution. Part B, identify the runaway solution, explain mathematically why it is considered unphysical. Part C, determine the physically acceptable solution by imposing the correct boundary condition, discuss the issue of pre-acceleration. Part D, using the Larmor formula, P sub RAD equals Q squared A squared over 6 pi epsilon naught C cubed. Compute the total energy radiated, E sub RAD equals the integral from 0 to infinity, P sub RAD of T dt. Part E, starting from the equation of motion, derive the energy conservation law. Show explicitly that external work is partitioned into mechanical, kinetic energy, radiated electromagnetic energy, and near-field shot energy. Identify the shot energy term. And part F, discuss the physical limitations of the Abraham-Lorentz force equation, address runaway solutions, pre-acceleration, classical point particle self-energy divergence, and limitations of the classical approximation. Okay, so this is a radiation reaction and energy conservation problem. So beginning with part A, prerequisites here for part A. The Abraham-Lorentz equation is ma equals F sub ext plus q squared over 6 pi epsilon naught c cubed a dot. The external difference is F sub ext equals F naught e to the negative gamma t x hat. And if we define the radiation reaction time, tau equals q squared over 6 pi epsilon naught mc cubed. So then we can make the equation A equals F sub ext over m plus tau a dot. So from here, what we can do is, since the force is along x, the motion is one-dimensional. And A equals F naught over m e to the negative gamma t plus tau a dot. If we rearrange this, a dot minus 1 over tau a, that equals negative F naught over m tau e to the negative gamma t. So for general solution component, what we want to do is we want to solve a dot minus 1 over tau a equals negative F naught over m tau e to the negative gamma t. The homogeneous solution is going to be a sub h equals c e to the t over tau. And try a particular solution, a sub p equals a e to the negative gamma t. Then that would mean a sub p dot equals gamma a sub p dot equals gamma a e to the negative gamma t. If we substitute this negative gamma a e to the negative gamma t minus 1 over tau a e to the negative gamma t, okay, that's going to wind up equaling negative F naught over m tau e to the negative gamma t. So from there, we could say A times the quantity times the quantity gamma plus 1 over tau, that equals F naught over m tau. So A is going to equal F naught over m times the quantity 1 plus gamma tau. And for A of t, that's going to equal CE to the t over tau plus F naught over m times the quantity 1 plus gamma tau e to the negative gamma t. So that's part A. Okay, and now part B. Let me just change this. So going back, well, part B from the first page, what they want us to do for part B is identify the runaway solution and explain mathematically why it is considered unphysical. So part B here, the runaway solution, the term CE to the T over tau, that's going to grow exponentially as T approaches infinity. And this is the non-physical runaway solution. So a physical solution must set C equal to 0 if the force is assumed to act for T is greater than or equal to 0. And the acceleration must remain finite at late times. Thus, we could say the non-runaway acceleration is A of T equals F naught over m times the quantity 1 plus gamma tau e to the negative gamma t. Okay, so building on that, that's letter B. Letter C, what they want us to do is determine the physical acceptable solution by imposing the correct boundary condition. Discuss the issue of pre-acceleration. So for letter C, the physical boundary condition here for A of T does not approach as T approaches infinity. So this remains the runaway term. So A sub PHYS of T equals F naught over M to, times the quantity 1 plus gamma R e to the negative gamma T. So also we could say the Abraham-Lorentz equation can also produce the pre-acceleration if the force is switched on suddenly. And for this problem, treating the force as defined for T is greater than or equal to 0, the non-runaway solution above should be shown. Okay, that's just a note. So that's letter C. So for here, letter D, it says using the Larmor formula P sub rad equals Q squared A squared over 6 pi epsilon naught C cubed. Compute the total radiated for E sub RAD equals the integral from 0 to infinity P sub RAD T of T to the dt. Just if you want to go back here, this is letter D. Okay, so letter D. So here, the total radiated energy, the Larmor radiated power is P sub RAD equals Q squared over A squared, divided by 6 pi epsilon naught C cubed. And using tau equals Q squared over 6 pi epsilon naught MC cubed, we could write P sub RAD equals M tau A squared. Substitute A of T equals F naught over M times the quantity 1 plus gamma tau e to the negative gamma T. Then P sub RAD of T equals M tau times this quantity F naught over M times the quantity 1 plus gamma tau squared e to the negative 2 gamma T. So the total radiated energy from T equals 0 to T equals infinity is E sub RAD equals 0 to infinity P sub RAD of T dt. And then so E sub RAD equals tau F naught squared over M times the quantity 1 plus gamma tau squared times the integral from 0 to infinity e to the negative 2 gamma t dt. And since from 0 to infinity e to the negative 2 gamma t dt is 1 over 2 gamma, then E sub RAD is tau F naught squared over 2m gamma times the quantity 1 plus gamma tau squared. So that's for letter D. For letter E, starting from the equation of motion, derive the energy conservation law. Show explicitly that external work is partitioned into mechanical energy, radiated electromagnetic energy, and near-field shot energy. Identify the shot energy term. So for energy conservation, we're going to start from M equals A equals F sub EXT plus M tau A dot. Dot both sides with V. MA dot V equals F sub EXT dot V plus M tau A dot V. Derivative of K with respect to T equals MA dot V. So dk dt equals F sub ext dotted with v plus m tau a dot dotted with v. And if we use this identity, ddt a dot v, a dot dotted with v plus a dot a, okay, equals that, right? So this equals this. So a dot dotted with v equals ddt a dot v minus a squared. Substitute dk dt equals f sub ext dotted with v plus m tau ddt a dot v minus m tau a squared. And m tau a squared equals p sub rad. Therefore, dk dt equals f sub ext dotted with v plus m tau ddt a dotted with v minus p sub rad. Now, building on that, we could say f sub, see if this holds, f sub ext dotted with v, that equals dk dt minus m tau ddt a dot v plus p sub rad. So f sub ext dotted with v equals ddt bracket k minus mta dotted with v close bracket plus p sub rad. And the term u sub shot equals negative m tau a dotted with v. That's the shot energy associated with energy stored reversibly in the near electromagnetic field. Thus, energy conservation is external power equals rate of change of mechanical plus near field energy plus radiated power. Okay, so that's letter E. Letter F, they want us to discuss the physical limitations of the Abraham-Lorentz force equation, address runaway solutions, pre-acceleration, classical point particle self-energy divergence, and limitations of the classical approximation. Okay, so let's see what we could do here. So in this situation, sorry about that. The Abraham-Lorentz equation is useful but problematic. Its limitations include runaway solutions, include runaway solutions, pre-acceleration, small tau approximation, and classical point particle idealization. So for runaway solutions, the homogeneous CE to the T over tau grows exponentially without bound. Okay, sorry about that. The pre-acceleration, runaway solutions, the homogeneous C to the E, CE to the T over tau grows exponentially without bounds. For the pre-acceleration, when the runaway is removed, using future boundary conditions, the particle could begin accelerating slightly before the force is applied. For the small tau approximation, the theory assumes radiation reaction is a small correction. It is valid only when forces vary slowly over times much larger than tau equals q squared over 6 pi epsilon naught mc cubed. And for the classical point particle idealization, a point charge has divergent self-energy in classical electrodynamics. The equation is therefore not a complete fundamental theory and neglects quantum electrodynamic corrections and therefore fails near relativistic high field regimes. Okay, so that's all for this one. Thank you very much. Have a great day.